So welcome everybody with a new tutorial video. So in this tutorial, basically what we will see. So in this tutorial, basically we will see that. So common source amplifier with that connected load. So if you see that, the circuit. So this is M1, NMOS. And this is M2, PMOS with that connected configuration. And this is the output. And this is the input, V in. So as we remember that the M1 and M2 both MOSFET, we need to operate in region 2. So M1 and M2, the operating point will be region 2. So region 2 means saturation region. Saturation region. So if you see that for the M2 MOSFET, this is the gate, this is the drain, and this is the source. Right. And we know that for a diode-connected load, this is always in saturation. This is always in saturation region. That means region 2. So how to it's always region 2? Let us discuss about these things. So we know that the condition for the saturation is nothing but VGS minus VTH should be less than is equals to VDS. So here you can see that the VGS and the VDS, they are connected togetherly. So you can write that VDS minus VTH is less than is equals to VDS. So actually you subtract something with VDS, you can see that you always get a less value from VDS because you subtract some value with respect to VDS. So you always get lesser value than VDS. So you can see that your MOSFET is always in region 2. That means in saturation region. So now the question is that what is the voltage gain of this amplifier? This is the question. So to find out the voltage gain of the amplifier, we need to find out the output resistance of this configuration or the diode-connected common source amplifier. So let me just show you how we can find out the voltage gain of this particular circuit. So let me just clean the page. So if you want to find out the voltage gain of the circuit, so as it is, you know that it is a common source amplifier. The gain of the common source amplifier is minus GM into R out. So here GM is the transconductance of the driver MOSFET. So here the M1 is our input device or our driver MOSFET. So we get the GM of the driver MOSFET, which is GM1. So we can write that minus GM1 into R out. But what is the output resistance? So if you see from the output side to there and from output side to here, you can find out the output resistance. And by the way, this is your VDD. So as it is the previous tutorial, I discussed that the output resistance of the diode connected load is something. So if you consider the channel length modulation, so if you consider the channel length modulation, that means lambda is not is equals to 0. That means your RO is finite. So in that case, your R out of n will be, so R out of n will be 1 by GM2, because this is M2 MOSFET, 1 by GM2 parallel RO2, and the R out of n will be, R out of n will be RO1. So what is the total output resistance you feel? So you feel that, so this will be R out P for PMOS. So this is for PMOS. So this will be R out P, and this is for NMOS. So this is for PMOS, and this is for NMOS. This is for PMOS. So the total R out will be R out PMOS parallel R out NMOS. So if you see that your R out PMOS is 1 by GM2 parallel RO2, and then parallel R out N is, which is RO1. So basically this is your output resistance. You can feel from the output side of this particular amplifiers. So now you put the value in this equation 1. So from equation 1, you can write that is the voltage gain AV is equals to minus GM1 into R out is nothing but 1 by GM2 parallel RO2 parallel RO1. So basically this is your voltage gain equation of this particular common source amplifier with diode connected load. And in this case, your input device is basically NMOS, and your driver MOSFET is M1. But what happened if you not consider the channel length modulation? Then what will happen? Let's try to understand this one. So you have the equation of the voltage gain so far, which is minus GM1 into RO1 parallel RO2 parallel 1 by GM2. So if you neglect the channel length modulation, that means lambda is not is equals to 0. And your basically, this is my mistake most probably. This will be lambda is equals to 0. So lambda is equals to 0, and RO will be infinite because this will be very large value. So in that case, your RO1 and RO2 is actually very, very greater than in terms of like GM2. So we know that a larger value or a larger impedance parallel with a small impedance parallel, whenever they together, the small value is win. A small value is win in that cases. So as we neglect the channel length modulation effect, in that case, we write our modified equation of our gain, which is minus GM1 into 1 by GM2. So you can write that the gain is equals to minus GM1 divided by GM2. So this is another expression you can use as if it is the voltage gain equation for the particular common source amplifier with diode connected load. So if you want to do the further simplification, Let us write the AV is equals to, we get so far, minus GM1 divided by minus GM1 divided by GM2. So you know that the GM is equals to square root of 2ID in for GM1 is NMOS and GM2 for PMOS. So you can write mu n COX W by L of N divided by square root of 2ID mu PCOX W by L of P. So you see that from the circuitry, the current is same, which is ID, flowing the same current through the M2 and the M1 MOSFET. So you can cancel this square root and this 2 and this ID, and finally you have mu n COX W by L of N divided by mu P COX W by L of P, and with a minus sign here. So this is another voltage gain equation you can use for the particular MOSFET, particular common source amplifier with that connected load. And we know that the mobility of the NMOS is greater than the mobility of the PMOS. So NMOS, the majority carrier is electron, and PMOS, the majority carrier is hole. So we know the mobility of the electron is higher than holes. By using this concept, your mu n COX value is greater than from the mu P COX value. And by depending on your W by L ratio, you can tuning your gain. If your W by L of P is less than W by L of N, you get a higher gain, or you can increase your gain. But your W by L P is greater than from W by L of N. In that case, your gain will be little bit reduced. So this concept is very, very important to understand this scenario. And in this case, we are consider our driver MOSFET as NMOS. But if you consider your driver MOSFET is now PMOS, now what will happen? So you consider a PMOS, and this is your M2, and this is your VDD. And now you consider the NMOS as a diode connected load. So your gate and drain must be short, and this is your M1, and this is your V out, and this is your V in. So question is that what will be the voltage gain in this case? So similarly, you get AV is equals to minus GM2, because now your driver MOSFET is M2. So for this case, you consider the transconductance of this M2 P MOSFET, and the R out will be same. If you consider the channel length modulation, it will be RO1 parallel, RO2 parallel 1 by GM1. So if you neglect the channel length modulation, you get minus GM2 into 1 by GM1, which will be minus GM2 divided by GM1. And if you put the value of the GM in this equation, finally you get mu PCOX W by L of P divided by mu N COX W by L of N. So this is your voltage gain equation for the common source amplifier with diode connected load. Whenever your input device is basically PMOS. This is the voltage gain equation for the PMOS driver MOSFET and NMOS as a diode connected load. So I think everything is understandable. And with this, I conclude this tutorial. Thank you.